Hello everyone, welcome back to MP Coding. Today, I am going to talk about memory allocation mechanisms that we commonly use in Linux device driver development. In this video, I will mainly talk about kmalloc, kzalloc, and vmalloc. These are the most commonly used memory allocation APIs in kernel driver development. After that, I will explain GFP flags. And finally, I will give you an overview of the slab allocator. To fully understand these topics, we need to have a basic idea about virtual memory. I believe most of you already know about this, so I am not going to deep dive into the fundamentals of the system memory allocations. However, I have added explanations about virtual memory in the README file. There, you can read about why we need virtual memory, how it works, how pages and page tables work, what the TLB is, and what multi-level page tables are. I have also added some good reference links, so you can explore these topics on your own. If you are not familiar with virtual memory, I recommend pausing this video and first getting a basic understanding of how memory works in modern systems. There are many good videos and reading materials available online. Alright, let's move on to our main topic, Linux kernel memory allocation. The Linux kernel also runs in a virtual address space, just like user space programs, but it follows a different set of rules. Now, let's look at the main differences between user space virtual memory and kernel space virtual memory. In user space, each process has its own private virtual address space. This means every process is isolated from others. In kernel space, there is a single, global virtual address space shared by the entire kernel. All kernel code and kernel data use this same address space. Another important difference is memory paging. In user space, memory pages can be freely paged out to disk when the system needs more memory. In kernel space, most memory allocations must stay in RAM and cannot be paged out. This is because the kernel must always be able to access its memory immediately. Finally, let's talk about stability. If a memory error happens in user space, it usually affects only that one process. The operating system can simply terminate it. But if a memory error happens in kernel space, it can crash the entire system. That is why kernel memory management must be handled very carefully. Next, let's look at why GFP flags exist. To understand this, we first need to know that the Linux kernel divides physical memory into different zones. These memory zones exist because some hardware components have specific memory access limitations. In simple terms, not all devices can access all physical memory. Because of this, physical RAM is divided into multiple zones. For example, there is zone DMA, which is used for legacy DMA-capable devices. There is zone DMA32, which is used by devices that can only access the lower 32-bit address range, and zone normal, which contains most of the directly mapped memory used by the kernel. On some systems, there is also zone high memory, which represents memory that is not permanently mapped into the kernel's address space. It is important to note that not all zones exist on every system. For example, on most 64-bit systems, zone high memory is not used because the kernel can directly address all available physical memory. So, when the kernel allocates memory, it must know from which zone the memory should come. This is where GFP flags come in. GFP flags tell the kernel how and where to allocate memory based on hardware requirements and memory management rules. GFP flags also act as action modifiers. I'll cover those in just a minute. Okay, let's look at kmalloc. Kmalloc allocates physically contiguous memory. This means the memory is placed in one continuous block of physical RAM. Kmalloc is fast, it is DMA safe, and it works very well for small memory allocations. However, it can fail when the system memory is highly fragmented because it cannot find one large contiguous block. Why does contiguous memory matter? Some hardware devices, especially DMA-based devices, require physically contiguous memory. Certain hardware registers also expect memory to be contiguous. You can think of kmalloc as asking for one solid block of RAM, with no breaks allowed. Now let's look at kzalloc. Kzalloc is very similar to kmalloc, but the allocated memory is initialized to 0. This helps avoid uninitialized memory bugs and makes kzalloc safer, especially when working with structures, and kmalloc for allocating raw buffers. Next, let's look at vmalloc. Vmalloc allocates virtually contiguous memory, but this memory is not physically contiguous. This makes vmalloc suitable for large memory allocations, especially when physical memory is already fragmented. However, vmalloc is slower than kmalloc because it requires additional page table mappings. Vmalloc is not DMA safe, since the physical memory is not contiguous. Vmalloc works because of paging. Virtual memory hides physical memory fragmentation. A simple rule of thumb is this. If hardware needs to directly access the memory, use kmalloc. If the memory is used only by the CPU, use vmalloc. Okay, now let's look at GFP flags action modifiers. GFP flags control how the kernel is allowed to allocate memory. I have explained how memory zonce works. Now let's look at some of the most commonly used action modifiers. GFP kernel is the most common flag. It is used in normal process context, and it is allowed to sleep. GFP atomic does not allow sleeping. It is mainly used in interrupt context or other atomic contexts. GFP no wait tells the kernel to fail the allocation immediately if memory is not available. As I mentioned earlier, GFP DMA forces the allocation to come from the DMA memory zone. Now, here is a critical driver rule. Never use GFP kernel in an interrupt context. If you are allocating memory inside an interrupt handler, always use GFP atomic instead. If you look at the GFP definitions in the kernel header file gfp_types.h, you can see a full list of available GFP flags. I'm not going to explain all of them here. You can search online for more details, or you can read the explanations provided in the here. Now, let's talk about the slab allocator. First, let's understand why allocating full pages is not enough. The kernel already knows how to allocate memory in pages, usually 4 kilobytes per page. This works very well for large memory allocations. But kernel data structures are often very small. For example, credentials may be only around 16 bytes. Mutexes or locks are usually a few tens of bytes. Thread or task structures are a few hundred bytes, and a process structure is roughly 1 kilobyte. If we used a full 4 kilobyte page for each of these small objects, it would waste a huge amount of memory, be very inefficient, and cause severe internal fragmentation. Because of this, the kernel needs a memory allocator that works below the page level. This is where the slab allocator comes in. The core idea of the slab allocator is very simple. A single page should contain only objects of the same type. This single idea solves many problems at once. For example, one page may contain only mutex objects. Another page may contain only node objects. Another page may contain only task structures. Because all objects have the same size, there is no external fragmentation. Memory access becomes cache-friendly, and allocation and deallocation are much easier to manage. This is the main reason why the kernel uses a slab allocator. In modern Linux systems, the slab allocator implementation used is called SLUB. All memory allocation discussions in this video refer specifically to the SLUB allocator. I have added a more detailed explanation of the SLUB allocator in the README file. I have also included some useful reference links at the bottom. I highly recommend reading those if you want a deeper understanding of how the slab allocator works. This tutorial is mainly based on example code, so I am not going too deep into theory. However, having a basic idea of how memory allocation works is important to understand the code properly. Okay, now let's look at the code. I have created a new example, so let's go through it. At the top of the file, I have declared 3 character pointers. One pointer is for kmalloc, one for kzalloc, and one for vmalloc. These pointers will store the addresses returned by each allocation method. Next, I define two allocation sizes. Alloc size small is defined as 1024 bytes, which is a small memory allocation. Alloc size large is defined as 1 megabyte, which represents a large memory allocation. These are for slab allocation. I will explain that part when we talk about slab allocation. If you have been following this series, you already know about kmalloc, because we have used it a couple of times before. Here in the init function, I allocate memory using kmalloc. I pass the small allocation size and the GFP kernel flag. This means the memory is physically contiguous and the allocation is allowed to sleep. After that, I check whether the allocation failed. If kmalloc returns null, I print an error message and return an error code. If the allocation is successful, I print the virtual address returned by kmalloc. I also print the physical address, using this virtual to physical function, just to show that this memory is physically contiguous. kzalloc works exactly like kmalloc, but it initializes the allocated memory to 0. If kzalloc fails, I print an error message and jump to the cleanup label to free the previously allocated memory. Finally, let's look at vmalloc. Vmalloc allocates virtually contiguous memory, and it is suitable for large allocations. Here, I use the large allocation size, which is 1 megabyte. If vmalloc fails, I print an error message and jump to the cleanup label. If it succeeds, I print the virtual address returned by vmalloc. It is important to understand that kmalloc internally uses the slab allocator. If you look at the kmalloc function definition, you can see that it is implemented on top of the slab allocator, and the definition is located in the slab.h header file. Kmalloc is the standard method for allocating memory for objects smaller than a page in the Linux kernel. Under the hood, kmalloc selects an appropriate slab cache based on the requested size, and then returns an object from that cache. Another important detail is memory alignment. The memory returned by kmalloc is always properly aligned for the target architecture. At a minimum, the address is aligned to arch kmalloc -line bytes. If the requested size is a power of 2, the alignment is guaranteed to be at least that size. For other sizes, the alignment is guaranteed to be at least the largest power of 2 divisor of the requested size. This alignment guarantee makes kmalloc safe to use for most kernel data structures and hardware-related buffers. Now, let's look at a direct slab allocation example. Here, I create a custom slab cache using this function. The first parameter is a string name. This name is used in the /proc/slabinfo file to identify this slab cache. The second parameter is the size of the object stored in this cache. In this example, each object has the type my_object, which is defined at the top of the file. This structure contains an integer ID and a character array for a name. Next, the alignment parameter is set to 0. This means the kernel will choose a default alignment. The next parameter is the flags. Here, I use slab HW cache align, which aligns objects to the CPU cache line size for better performance. The final parameter is the constructor. I set it to null, so no constructor function is used. If this call is successful, kmem_cache_create returns a pointer to a kmem_cache structure. If it fails, it returns null. I store this pointer in the my_cache variable, which is a pointer to a kmem_cache structure. If my_cache is null, I jump to the cleanup label to free the previously allocated memory. If the cache creation is successful, I then allocate an object from this slab cache. I call kmem_cache_alloc and pass the cache pointer and the GFP_kernel flag. This returns a pointer to a my_object structure. And this object1 is defined here in the top as my_object pointer. If the allocation fails, I jump to the cache cleanup label. If it succeeds, I initialize the object. I set the ID field to 1 and copy a string into the name field. Finally, I print the address of the allocated slab object using pr_info. Now, you might be wondering what happens if I allocate more objects of type my_object, just like object 1. When I allocate the first object, the slab allocator creates a slab, which is usually backed by one or more pages. That slab is then divided into multiple objects of the same size. So, when I allocate object 2, object 3, and so on, the kernel does not allocate new pages every time. Instead, it simply returns another free object from the same slab. Only when the slab becomes full does the allocator create a new slab and allocate additional pages. This is one of the main advantages of the slab allocator. Object allocation becomes very fast, memory fragmentation is reduced, and memory reuse is efficient. So, allocating many objects of the same type is cheap and scalable when using slab caches. Okay, now that you understand how memory is allocated, let me show you how to properly free this memory. In this example, I use labels to handle errors that may occur during allocation. If an error happens, the code jumps to the appropriate label and free any memory that was already allocated. This ensures that no memory leaks occur. For memory allocated using kmalloc and kzalloc, I use the kfree function. For memory allocated using vmalloc, I use the vfree function. And for slab cache allocations, the cache is destroyed using kmim_cache_destroy. This order ensures that resources are released correctly. The same cleanup logic also applies in the module exit function. In the exit function, I free all allocated memory again, to make sure nothing is left allocated when the module is removed. I free the kmalloc memory, the kzalloc memory, and the vmalloc memory. Also free the slab object using kmim_cache_free, and then destroy the slab cache using kmim_cache_destroy. Finally, I print a message to indicate that all memory has been freed. Okay, now let's build the module. Open a terminal and navigate to the source folder. Type make and press enter. You can see that the build has completed successfully. Now, let's load the module. Before doing that, in another terminal, open the kernel message buffer by typing dmesc -w. This allows us to watch kernel messages in real time. Now, load the module by typing sudo insmod memory_alloc.ko and press enter. Here is the output printed in the D message buffer. You can see that kmalloc successfully allocated memory, and both the virtual address and the physical address are printed. This confirms that kmalloc returns physically contiguous memory. Next, kzalloc also allocated memory successfully. Only the virtual address is shown, because kzalloc behaves the same as kmalloc, but initializes the memory to 0. Then, vmalloc allocated memory successfully. Notice that the vmalloc address comes from a different virtual address range. This indicates that the memory is virtually contiguous, but not physically contiguous. Finally, the slab object was allocated successfully. This address comes from the custom slab cache we created sing kmim_cache_create. Overall, this output confirms that all memory allocations worked as expected. Okay, now let's unload the module. In the terminal, type sudo rm mod memory_alloc and press enter. You can see the message, memory freed, in the kernel log. This indicates that all allocated memory was freed successfully when the module was unloaded. Additionally, if I show you the /proc/meminfo file, you can see how memory usage changes at the system level. This file gives an overview of the current memory state, including kernel memory usage, slab allocations, and available memory. You can use this information to observe how memory is allocated and freed when loading and unloading kernel modules. Also, if we look at the /proc/slabinfo file, we can see detailed information about slab caches in the kernel. Here, you can find entries for both built-in kernel slab caches and the custom slab caches. This allows us to observe how many objects are allocated, how many are free, and how slab memory is managed internally. Now, let's load the module and check what happens to the slab information. Before loading the module, let's first look at only the kmalloc 64 slab cache. I do this by running this grep command. Now, let's load the module. In this example, I created a custom slab cache called my_cache, so you might expect it to appear in slabinfo. However, if you look at the slabinfo again, you can see that my_cache does not appear. But if you check kmalloc 64 again, you will notice that its values have changed. Some new allocations appear there. So what is happening? Modern Linux kernels use the SLUB allocator. One of its optimizations is called slab cache merging. If the size of objects in a custom cache matches a common size, such as 32, 64, 96, or 128 bytes, SLUB may silently merge that custom cache with an existing kmalloc cache. In my case, the size of my_object matches the kmalloc 64 cache. So SLUB merges my_cache into kmalloc 64 automatically. That is why my_cache does not appear as a separate entry in slabinfo. Now, if we want to prevent this behavior, we can use the slab no_merge flag here when creating the slab cache. Add the flag slab_no_merge. Let's unload the module first. Then, I rebuild the module with the new flag. Okay, now load it again. Here you can see loaded successfully. If we check slabinfo again, we can now see that my_cache appears as a separate slab cache. This is how we can tell the kernel that we want a separate cache for our custom objects. And that brings us to the end of today's video. Today, we looked at the kernel memory allocation mechanisms. We discussed kmalloc, kzalloc, and vmalloc. We also looked at what GFP flags mean, and finally, we explored slab allocation and how it works internally. In the next video of this series, we will discuss kernel linked lists. Thank you very much for watching. Stay tuned. If you found this video useful, please like, subscribe, and share it. See you in the next video.